Hi everyone, my name is Guy, and I'll be telling you about our joint work with Jane and Lee Young on learning stochastic decision trees. So to start off, I'm going to describe a very classic problem, decision tree learning, for which we tackle a generalization of it. So in decision tree learning, we're given access to some labeled data set. In the entirety of this talk, all features are Boolean. So each example is just a Boolean string indicating the value of various features. And then the output is the classification of this example. It's f of x, which also is assumed to be 0 or 1. And then the goal is to output a decision tree that computes this function f or approximates it well. And now by decision tree, I just mean what you probably naturally think of when you think of a decision tree. So at each node, we have a particular feature. So the root here is the feature x1. And then that node reads the value of that feature, and if it's 1, we go to the right subtree. If it's left, we go to the 0 subtree. We continue reading features in this manner until we end up at a leaf, and then we output the value of that corresponding leaf. Okay, so this is a really classic problem. I've included just a smattering of citations here, but there's been more than 30 years of research and many dozens of publications on this problem and variants of it. One particular variant that will be important for us is this notion of proper learning. So if you consider non-proper learning, we might assume our data comes from a decision tree, but then we don't actually have to output a hypothesis that is itself a decision tree. We just have to output some function that well approximates the function that our data set came from. In proper learning, we're actually require the output of our algorithm to itself be a decision tree. And there are many reasons why this might be desirable in general, but for decision trees, it's particularly important because decision trees have a lot of really nice structure. So for example, if you're a machine learning practitioner and you want to have an explainable classifier, decision trees are one of the canonical examples of what an explainable classifier is. So proper learning is particularly important for decision trees. Okay, so now what do we actually study in this talk? In this work, we study stochastic decision trees. So there are generalization of decision trees where nodes don't just, in addition to just splitting on a feature, nodes can also be a biased coin flip. So for example, in this decision tree, the root is a 0.7 biased coin flip. We use this $sign to indicate coin flip. So with probability 0.7, we move to the right subtree. With probability 0.3, we move to the left subtree. These nodes can be interspersed throughout the decision tree. So this one has 2 stochastic nodes. And each of them can have different biases. So the second one is a 0.2 biased coin flip. There's been a line of work exploring stochastic generalizations to normal models and how you can learn them. So a reason this is useful is that many natural processes to generate data are stochastic in nature. They might be stochastic because there's actually randomness, or they might be stochastic because we don't have enough features to fully determine the label. So for example, consider us wanting to predict whether it rains tomorrow. We might have access to only like some limited features. Maybe we know the temperature today, and we know whether it rained today, and maybe, I don't know, we know whether there's a mountain nearby that might influence the likelihood it rains. But, given these 3 features, we don't have enough to fully determine whether it rains tomorrow, so we can imagine adding in some randomness to the final value. So given our features, the true answer might be, okay, there's a 70% chance it rains tomorrow. Okay, so the key thing in this model is we don't actually observe this 70%. Instead, we'll see the value of these features, and then we'll observe that, okay, it did rain or did not rain. So we kind of observe the coin flip, but we don't know the probability that coin flip was a 1. And then our goal is, so we get to observe lots of these inputs x, and then either a 0 or 1 according to the appropriate probability. And then our goal could be to learn a model that kind of simulates this generative process. Okay, our first result is an algorithm for learning stochastic decision trees. So there's an algorithm which, given an error parameter epsilon and random samples from a stochastic decision tree t, which is size s, it runs in time quasi-polynomial. So here this n is the number of features, this s is the size of the decision tree, and this epsilon is kind of our accuracy parameter. And with high probability, it outputs a deterministic decision tree H, such that the probability H is not equal to T is at most opt plus epsilon. So I need to interpret this. I haven't yet defined what opt is or why this decision tree is deterministic. So opt is the Bayes optimal error. It's the best error of any possible function with respect to this stochastic process. And the reason opt isn't zero is suppose our stochastic process is just 1 70% of the time and zero otherwise. Then no matter what we return, regardless of whether it's randomized or deterministic, the best error we can hope for is 70%. The smartest thing to do is to output 1, which is correct 70% of the time. So opt is the best possible error we can achieve, and it can be achieved deterministically. Now, and then epsilon is just kind of this additional error parameter we want. So that's why we output.
Great, thank you, Guy. Let's dive right into the proof of theorem 1. Our main technique is the approximation of stochastic decision trees by stochastic leaf decision trees, which are decision trees whose internal nodes must all be deterministic queries, but can have one stochastic transition at the end of each path whose bias is mu t of x, which is defined to be the expected value of t of x taken over the randomness of t. A stochastic leaf decision tree can be thought of as a deterministic decision tree with real-valued leaves, labeled by mu t. This allows us to leverage an algorithm by Mehta and Raghavan, which properly learns deterministic decision trees, including those with real-valued leaves. Furthermore, this algorithm is robust to adversarial noise. So here's a formal statement of our stochastic leaf lemma. Let T be a stochastic decision tree of size S and epsilon be an error parameter. Then there is some tree T prime, which has the stochastic leaf property and is size S to the O of 1 over epsilon squared. And its absolute value distance from mu T is at most epsilon. So the proof is quite straightforward, so we can actually do it in a fair bit of detail. Let M be the number of stochastic transitions in T. We will interpret each of these stochastic transitions as a query to a second input, which we will call R, from 0, 1 to the M. And that is the value of T of X for some X and some R, it's the value of T of X with the stochastic transitions fixed by R. Then we draw R1 through RC, which will fix C later, but these are C uniform random strings from 0, 1 to the M, each of which represents a random fixing of the stochastic transitions in T. Then we define our estimator, which is this random variable, the expected value of T of X and Ri. You can basically think of it as a sample mean for C independent trials of T, run once for each value of Ri. So we get a couple of good properties of our estimator by the fact that the Ri's are independent. First is that the expected value of the estimator, taken over the random draws of R1 through RC, is just the expected value of T of X comma R, where R is drawn uniformly at random, and that is, by definition, mu T of X. And the variance of the estimator, by independence, is 1 over C times the variance of T X comma R. Now, since T is 0, 1 valued, the variance of T of X comma R is at most 1/4, and so the variance of the estimator is at most 1 over 4C. Now we can set C to be 1 over epsilon squared. Then for any fixed X, the variance of the estimator is at most epsilon squared over 4 because of the setting of C. And just by definition of variance, that's also the expected squared distance between the estimator and mu T of X. Then square root both sides, and we get that the absolute value distance is at most epsilon over 2. But this is still for a fixed X, and the expectation is over the randomness of R1 through RC. So now we take one more expectation over all X and swap the expectations, and we get that the expected value of the expected absolute value distance between the estimator and mu T is at most epsilon over 2. Now, since there's got to be some event that puts this quantity, this random variable, at most its expectation, this means that there exists some values of R1 through RC such that this inner part, this random variable, is at most epsilon over 2. We will call these special values R1 through RC star. And this here is just unfolding the definition of the estimator. It's the expectation over all of the Ri stars of T of x fixed by Ri star. So now all we have to do is build a decision tree, a deterministic one, that computes that computes the estimator. And the way we do that is just by stacking all of the deterministic trees on top of each other. So each T of Ri star represents T with the stochastic nodes fixed by Ri star. This gives us an internal portion with s to the 1 over epsilon squared deterministic nodes. It's s to the c, where c is 1 over epsilon squared. And we label the leaves with stochastic transitions with a bias of the estimator. So to sum up what we've just done, we've shown that for every stochastic decision tree of size s, there is a stochastic leaf decision tree of size s to the 1 over epsilon squared, such that the absolute value distance of their means is at most epsilon. And if you want, you can round these leaves to the closest 0 or 1 to get a deterministic decision tree whose error with respect to the first one is opt plus epsilon. So now let's go into the algorithm that will learn the stochastic leaf decision tree. So this is an algorithm by Mehta and Raghavan that has the following property. It takes as input some dataset x and a maximum depth d, and it outputs the decision tree with minimal error with respect to x among all depth d decision trees. And to get around this depth parameter, because we're using size as our main parameter, it is just a true fact that if T is a size S stochastic decision tree, there is a depth D decision tree for D equals log S over epsilon that is opt plus epsilon close to T. And you get that by just cutting off all of the paths that are longer than D and replacing them with arbitrary leaves. So Mehta and Raghavan is actually an optimization of this algorithm, but for simplicity, we'll discuss the non-optimized version. It's defined recursively. The base case is when d equals 0 and you return the best constant. Otherwise, for each possible root, I in n, you call find to build the left and right subtrees of the tree rooted at xi, and let the resulting candidate tree be called ti, and then minimize over the ti's and return the one with minimal error with respect to x. So the proof that the tree returned by this algorithm is optimal is a pretty straightforward induction on D. Basically, if find returns optimal trees for all of the depth D minus 1 calls here, and then you further minimize over all the depth D candidates, then you get a tree of minimal error among all depth D decision trees with respect to your sample X. Furthermore, we know that there is some decision tree with error at most opt plus epsilon for appropriately chosen value d based on our stochastic leaf lemma. That is a decision tree with error at most opt plus epsilon with respect to the true target stochastic decision tree. So if the sample is eta corrupted, then that decision tree has error at most opt plus eta plus epsilon on the corrupted sample. Then, by the optimality of the find algorithm, we get a tree with either that error or better. Then this tree must have error at most opt plus 2 eta plus epsilon on the uncorrupted sample, which is the guarantee that we want to give. And then the final error guarantee follows from standard generalization argument. And we also know that this find algorithm runs in time n to the O of d. This is by solving the recurrence relation. And to sum up our results, we get an algorithm that runs in time n to the d, where we're able to set d to be log s over epsilon squared by our stochastic leaf lemma. And with high probability, it outputs a decision tree with error at most opt plus epsilon if there's no corruption in the sample. But if there's corruption in the sample, then the hypothesis gets error at most opt plus 2 eta plus epsilon, which is information theoretically optimal. Thank you for watching.